Assalamualaikum and good day. My name is Nur Isalina Huda binti Nazri and I will be presenting our research project titled Pattern Recognition for RF Neural Signal Processing using Discriminant Clustering. This project is conducted under the supervision of Dr. Roshakimah binti Muhammad Isa and it is a collaborative effort with my research partner Muhammad Rashid bin Rusli. Nowadays, we use mobile phones all the time, and the radio frequency radiation produced may affect our brain activity. This project studies the effect using EEG signals, which record brain waves, especially in the alpha and beta bands, which link to relaxed vision and focus. But one main problem is that EEG data is very limited, and this makes it hard for machine learning to give accurate results. So, in this study, I will implement synthetic data to create more brainwave samples to help the system learn better and improve classification accuracy by genders. There are three objectives for this study. The first one is to identify the significant data characteristics in beta and alpha frequency bands for discriminant clustering of neural signals in this response to RF exposure across male and female groups. Second is to generate a synthetic data model that improves the range of EEG conditions to strengthen the classifier performance and accuracy. Third is to develop and optimize PAR by selecting the highest accuracy features for asymmetry analysis in the right and left hemisphere to ensure robust classification with using KNN. For the scope of work, for this project, I worked with 97 EEG samples from engineering background. The samples were divided into three RF exposure groups. With the first one is left exposure (LE), right exposure (RE), and then sham exposure (SE). The data went through statistical analysis using SPSS, and then I use MATLAB to generate synthetic data by adding ±10% random noise to the actual data, and the dataset of the actual and synthetic was then combined, and KNN classification was applied to observe brainwave patterns under the RF exposure. However, there are some limitations for this study. The first is all participants were from the same group, which is engineering field, and which the findings might not apply to the general population. And second, the study focused only on the short-term RF exposure but not on the long-term effects. For the methodology, Figure 1 here shows the overall workflow of the study, which in the pre-processing stage, first the power spectral density data was organized by gender, male and female, to compare the brain responses separately. And then I did data pre-processing using SPSS software. This step will remove outliers, and then all the data is normalized to make sure the values is easier to compare. And in the processing stage, I did feature extraction called Power Asymmetry Ratio (PAR). This value shows the difference in brain activity between the left and the right sides of the brain. Next, I use MATLAB to generate synthetic data by adding ±10% random noise to the actual data. The synthetic data was then validated by using Pearson correlation analysis to make sure it followed the same patterns as the actual data. For the statistical analysis, I used Levine test to check the variance and Welch ANOVA to find any significant changes in brainwave patterns between groups. I also applied linear discriminant analysis (LDA) to visualize the group separation. And finally, for the analysis, I used KNN, K-nearest neighbors classification to identify brainwave patterns before and during the RF exposure. On to the result and discussion. The first analysis I did for the combined data was Pearson correlation to compare the actual EEG data and the synthetic data created. This test checks how close the dataset both datasets follow the same pattern, which in other words, whether the synthetic data behaves like the actual one. In each graph, you can see here, the solid lines represent the real data and the dotted lines are the synthetic ones. As you can see, the lines follow almost the same trend. This shows a strong match between the real and synthetic signals. To support this, the Pearson R values are all high, which above 0.93, which shows a strong and significant correlation. This means that the synthetic data is reliable and can be used together with actual data in the analysis, and it can help to solve the problem of this limited real data in EEG research. The next analysis I did was on the Power Asymmetry Ratio, PAR. I calculated PAR using combined data and created these bar charts using Excel. as we can see, the largest brainwave changes occurred during the left exposure LE for both genders. Females show higher PAR values than males, showing a stronger neural response to RF on the left side. During right exposure, the changes were smaller, especially in females, which this shows that the right side might be less sensitive to RF radiation. And in the SE, there was almost no change because there was no real exposure. To conclude, LE caused the most significant brainwave response, especially in females, which aligns with past studies showing that left hemisphere dominance in engineering students. To check if the brainwave changes between groups were statistically significant, I used the Welch ANOVA in SPSS, which this test is more reliable when the data has uneven variances. For male participants, we can see that during exposure, the p-values were less than 0.005 for beta and alpha, meaning that the changes are statistically significant. For females, the alpha wave shows a very strong difference with p less than 0.001, but beta had a p-value of 0.263, so it is not significant. This supports the earlier PAR results, confirming that RF exposure affects alpha waves more and the effects are clearer in females, especially in the LE group. We need discriminant analysis, which I use LEDA in SPSS to support the results from PAR and Welch ANOVA tests by showing how brainwave patterns are grouped between left, right, and sham exposure. As we can see, before exposure, all groups are close and mixed for both male and female. But during exposure, we can see that the left exposure group moves clearly apart, especially in female participants. This means the brain shows a stronger reaction to left side and the change is more noticeable in females. Then, we can see here, right and sham exposure groups stayed almost in the same position on before and during, which it shows less effect. So overall, LDA helps confirm that left exposure has the strongest impact to support the earlier analysis. And then I use K and N in classification in MATLAB to classify brain activity under RF exposure. The data was split into 70% for training and 30% for testing, and I use Mahalanobis distance for better accuracy. I compare results using actual data only and the combined data. As you can see in the table here, for females during exposure, combined data give the best results. Training accuracy improved from 71% to 88%, and testing accuracy slightly improved from 65% to 66%. For males, we can see that the training improved from 71% to 80%, but testing dropped from 77% to 58%. This shows that synthetic data helps training, especially with limited real data. Also, left exposure was the easiest to classify. Overall, combined data boosted training, mainly for females, and made classification more stable. To conclude this project, this study shows that RF exposure can change brainwave activity, especially in the alpha and beta bands, and the effects are different between males and females. By using synthetic data, I was able to solve the problem of limited real EEG data, and this helped to improve the results. The final K&N classification using Mahalanobis distance gave the best performance, 88% accuracy for females and 80% for males. This proves that combining actual and synthetic data helps in detecting brainwave patterns more accurately. For future work, this study can be improved by using more diverse participants, trying other machine learning methods, and studying long-term RF effects. That's all from me. Thank you.